Good evening, everyone. Welcome back. This is Mr. Steele once again, here with another set of video solutions for you to help you work through tonight the problem set focusing on more implicit differentiation that extends our work with implicit differentiation to some slightly more difficult problems, to doing some algebraic work with the functions, to computing the second derivative, to writing the equations of the normal lines, as well as computing and finding the points where vertical and or horizontal tangent lines occur on particular implicitly defined graphs. So there's a bunch of little stuff to get through. The problem set has some challenging parts to it. Sometimes it's not even the difficult part. Sometimes implicit differentiation is actually the easiest part. But I want you prepared for all sorts of challenges that might get in there. And I'll even let you know that the hardest problem on this assignment was one that after doing a ton of work, probably a half hour of work writing, found out was literally impossible. So you got out of that one, but the rest of the ones here, these are good things. So let's not delay it any longer. Let's jump in to the first problem. And our first problem that we're going to attack is from the first section, of course, where we're asked to write the equations of the tangent and normal lines respectively to each implicitly defined curve at an indicated point or coordinate. I'm skipping 1 and 2 where the ordered pair is provided for you and where the differentiation is a little bit cleaner, but I'm going to do 3 and 4 for you where the work is a lot more involved, or at least a little bit more involved, to make sure that we've got all the elements here and that you can see everything working through. My hope is that if you're confused on 1 or 2, you can look at this video for number 3 and reason your way back through and do the slightly simpler problems, or the less complicated problems at the very least. So in this case, we've got the curve 5x plus 4xy squared equals 3y plus 15, and we want to figure out the equations of the tangent and normal lines to each curve when y equals 2. So since this is an implicit differentiation problem, I'm going to start with the implicit differentiation part. I want to take the derivative with respect to x of this entire equation. So we're going to do it on both sides, so that way we can maintain the balance that we have defined, and that will allow us to at least get a slope equation developed. That'll be a function of both x and y. So in here, the x terms, of course, as we mentioned before, are simple. This is just going to be 5. But when we get to the derivative with respect to x of 4xy squared, remember that's where the product rule is going to pop up, because we have an x variable, we have a y variable. We're going to have to handle that one, so we'll work on it in a second. And the other thing I'll remind you is that when you take the derivative with respect to x of an expression with a y in it, that can be a little bit challenging. Of course, the derivative of a constant, with respect to any variable, is 0. So those are easy. So as far as the pieces here, the big thing to remind yourself of, first and foremost, is when you're taking the derivative with respect to x of a function with a y in it, recall that the derivative itself is going to be the same derivative as if it were x. But because that y and x have an implicit connection to one another, we multiply using the chain rule by y prime. So this is really like 3y's derivative is 3, but the derivative of y with respect to x is y prime. Some places you'll also see that written as 3 dy dx, but both of these are acceptable, and y prime is just a little easier to compute with, as long as you keep your handwriting careful. So over on this side, we are going to have 3y prime as the right side. On the other hand, we have to deal with the fact that we have this 4xy squared problem. So to attack this one, we've got to look at it as a product. We're taking the derivative with respect to x of the product 4x times y squared. So using the product rule, we'll end up with the derivative of the first, so the derivative with respect to x of 4x times y squared, plus 4x times the derivative with respect to x of y squared. Simplifying as much as we can, we get 4y squared right here. On this next one, we get 4x, but then the derivative with respect to x of y squared is going to be first the derivative of y squared, which is 2y, and then times y prime. So with that said, we can bring that back over, and we'll end up with, on this side, 4y squared plus 8xy y prime. And of course, we can't forget that 5 that was there in the very beginning, so that we get 5 plus this expression from the product rule equals the expression that was just simply from implicit differentiation. So with those things both present, we can now get the y primes together and start to rewrite this. So I'm going to keep the 4y squared plus 5 on the left. I'm going to subtract the 8xy y prime over to the right side. We'll get 3 minus 8xy parentheses y prime. So what I do is I move the term over with the y prime, the other term with the y prime over, and then I factor it out as a GCF all in one swoop just to make sure that it simplifies things. And the cool thing here is that we end up with dy dx being equal to 4y squared plus 5 divided by, and again the divided by is because we want to get the y prime by itself, so we divide by 3 minus xy, 8xy. And so there is our slope. Now yesterday we might have stopped at that point and just said, okay, cool, We found our slope. We are done with this problem. But unfortunately, we're not done here because we're supposed to find the equations of the tangents and normal lines. So from here, the first thing we want to do is we want to plug in the ordered pair and figure out what that slope's equal to. Unfortunately, we have an issue if we try to do that in this particular problem. This is a challenging question here, particularly because we're only told that y equals 2. So unfortunately, what that means is we have to take that information about y being equal to 2 and we need to plug it back into our original relation to solve for what x is equal to. So plugging in, we have 5x plus 4x times 2 squared equals, 3 times 2 plus 15. So simplifying some stuff here, we're going to get 5x plus it looks like 16x is equal to 21. And combining some pieces together, we get 21x equals 21. In other words, x equals 1. So that now completes our work. We now know that the ordered pair we're interested in the tangent normal lines to is at x equals 1, y equals 2. So down here, we're going to evaluate this at the point 1, 2, plugging in x equals 1 and y equals 2 simultaneously. When we do, we get 4 times 2 squared plus 5, all over 3 minus 8 times 1 times 2. That's going to give us, it looks like 16 plus 5 is 21. In the denominator, it will be 3 minus 16, which is negative 13. So that tells us that the slope of the tangent is going to be equal to negative 13 over 21. So it's a lot of work to get to the slope. And the nice thing is once you've done all that work, you've got the first part of your answer done. The tangent line is going to have the equation y minus 2 equals negative 21 over 13, quantity x minus 1. For the normal line, everything about the normal line, recall, is exactly the same except for one thing. That would be the slope. If we want to figure out the normal line to an equation, and we know the tangent line's right here, the normal line is perpendicular to that tangent line at the point of tangency. So since it has to go through the point of tangency, we maintain that exact same x1 and y1 respectively. And for our slope, we end up with the perpendicular slope. So perpendicular slope, if you'll recall from Algebra 1, tells you that we get the negative reciprocal. So in this particular case, the negative reciprocal is going to be positive 13 over 21. And there is our normal line. So again, lots of little pieces in this first example. Obviously, this isn't a trivial problem. We had to take the derivative. We had to use the product rule. Like, of course, every implicit problem requires a little bit of chain, but the product rule popped in there. We got our derivative. Unfortunately, we only had one coordinate, so we had to plug that into our equation and solve for the second coordinate. Once we had it, we plugged it in to get the slope of the tangent line, allowing us to write said tangent line. And then for the normal line, we wrote the exact same equation, but with the negative reciprocal slope, so that the line would be perpendicular, but through that same point of tangency. And there is question number 3, also holding the places of questions 1 and 2, which are easier than this one. Okay, next that brings us to question number 4. Now, on the surface, question number 4 is basically the same thing as the last one. There's just a couple extra little wrinkles that have been tossed into this problem. So if you'll imagine, we're trying to find the equations of the tangents and normal lines when x equals 2 for this interesting looking function. So just like before, I'm going to begin by taking the derivative with respect to x of both sides. Now, one of these sides is way easier than the other one. I think you can probably tell that it's going to be the right side. The derivative of 2x with respect to x is 2, and the derivative of y with respect to x is just what we call y prime. On the left side, though, that requires the quotient rule. The reason being, we have a function on top of another function. Doesn't matter that they have mixed variables. They're still one on top of the other, so we need the quotient rule. I'm going to try to differentiate this one a little bit faster, though. Oh, no, you know what? I'll be careful here. So we can still use the song, though. Never a bad time to sing. Low, D, high. And yes, I know you could do this derivative in your head, whatever. Minus high, D, low. All over low, low. Quotient rule. Sorry. So there's our stuff. It's all equal to 2 minus y prime from our work on the right side. Taking the derivatives and kind of cleaning some stuff up right here for a second. Derivative with respect to x of 2x is just 2, so we'll get 2y minus 2x times the derivative of y with respect to x, which we call y prime. All of this is over y squared, And that's all equal to 2 minus y prime. Now from here, if we want to start solving this thing, we need to multiply both sides by y squared so that we can clean it out and clear it out of the denominator and start to get those y primes together. So when I multiply both sides by y squared, the left side just becomes 2y minus 2xy prime. The right side, I'm going to distribute it in so that we can isolate pieces better. We'll get 2y squared minus y squared y prime. Now I got to move everything together, so it's really your choice where you want to do that. I'm going to move these two pieces. I'm going to move the negative y squared y prime to the left side. I'm going to subtract the 2y from both sides. That's going to, I'm going to bring this up here. That's going to give us, let's see if I do this right, y squared minus 2x all times y prime. Notice once again, I've just factored out that GCF of y prime right off the bat. I just want to save myself a little bit of trouble. And it's all equal to 2y squared minus 2y. Pulling our pieces together, we'll get that y prime, which we know better as dy dx, is going to be equal to, I'll factor out the 2y, get y minus 1, all over y squared minus 2x. So there's our slope. Good job. That was an important point. We now know how to find the slope of the tangent line. So we'd prepare to start putting in that slope of the tangent line, but once again, sad panda for us, we only know that x equals 2. So we need to quickly find what the y-coordinate would be when x equals 2. So plugging in x equals 2, I'm going to do it a little bit faster. We're going to plug in a 2 right there and right there. We're going to get 4 over y equals 4 minus y. To solve this, I'm going to multiply both sides by y. You'll end up with 4 equals 4y minus y squared. If we move everything to the left side by adding y squared and subtracting 4y, we get y squared minus 4y plus 4 equals 0. And as a heads up, that is a perfect score trinomial. That just says y minus 2 squared is 0, which means y equals 2 also. So what we're going to be doing is we're going to be evaluating this at the point 2, 2. Now that sounds like a perfectly reasonable thing to do. We'll have 2 times 2 minus 1 all over 2 squared minus 2 times 2. Now your numerator, get happy, it's 4. Your denominator is 0. That's not the ideal outcome here. What we've just shown is that the slope is infinity. It's undefined. In a sense, what this is telling us is that we actually have a vertical tangent line. And I don't have room to write the word vertical tangent line, but we actually have a vertical line that forms the tangent here. In fact, that vertical line is the one x equals 2. So at this point, if we try to write the equations of that vertical tangent line, imagine what we're seeing here, whatever it is that's I'm trying to draw. So if we have the tangent line right there, we have a vertical tangent line, and then the normal line would have to be perpendicular, which makes it a horizontal tangent line. So in a sense, what we've just forced ourselves into is we just forced ourselves into two very simple tangent line and normal lines. The tangent line is simply going to be x equals 2. That will give us the exact line that we're looking for. The normal line, on the other hand, has to be perpendicular at the same point, and since we know we have to go through the point y equals 2, or x equals 2, y equals 2, the normal line is just going to be y equals 2. This is a really, crazy outcome. It's not something you would expect. It's not something that I expected either when I wrote the question. I was just coming up with interesting looking functions, but it turns out that in this case, our tangent normal lines are just x equals and y equal kind of expressions. So in any event, though, I'd say the most important thing here, that ending was pretty tough, but if you could get to this point, I think you're really on track for everything, and if you're able to reason out parts of that at all, you're in really good shape, because that was definitely a tough question. Okay, next, that brings us to the first, really intense new portion of our assignment in today's lecture, in today's lesson, which is computing the second derivative, d2y over dx squared. So that is the second derivative, or the second implicit derivative, if you want to call it that. In other words, we want that expression. I could talk about concavity for the function, or for the relation, or about, whether or not the slope is increasing or decreasing relative to the x and y axes. So in here, in order to get there, you'll have to recall that the progression we have to follow is first we need to compute dy dx, just like any derivative, and then after that we're going to compute the second derivative by taking the derivative with respect to x of that expression dy dx, and that will be equal to the answer we're looking for, d2y over dx squared. Now, unfortunately, this is going to be a challenge because so often dy dx ends up being something that requires the quotient rule or requires some extra chain, or it just takes a lot of work to get through there. So no, these can be challenging. And in fact, the next problem we go through, 6, is one of the most computationally challenging problems that we've seen in this course and may see for quite a while, just because of the amount of stuff that's there. So in this case, though, let's just jump right into it and get going. So, of course, to start, we want the first derivative, dy dx. So we're going to take the derivative with respect to x of 4x squared plus 3y squared equals 16. So differentiating, we'll get 8x plus 6y, but because we differentiate an expression with a y, we need the y prime, and all of that's equal to 0, because the derivative of a constant is 0. Now, looking at our pieces here, we can very quickly move some stuff over. We'll get 8x equals negative 6y y prime. It's going to lead us to y prime, otherwise known as dy dx, is going to be equal to negative 8x over 6y, which you probably better know as negative 4x over 3y. So there is our first derivative. That's a huge point to reach. So we've just found dy dx. So huge point to reach for sure. Like, congratulations, your life's going well, good job. But unfortunately, that's not going to do it for us. We want the second derivative. We want to start to look at concavity and things like that. So in other words, to move forward, what we're going to do, if I can do this correctly, what we need to do next, aside from get a little bit frustrated, really, come on, haha, tricked it. What we want to do next is we want to actually take the derivative with respect to x of both sides of this equation. Specifically because the derivative with respect to x of dy dx is exactly what we're looking for. This is going to give us d2y over dx squared, otherwise known as the second derivative of y with respect to x. So in doing so, again, as we said, this right side's easy. The left side's where the real work happens. And on the left side, we have negative 4x over 3y, which requires, yes, that's right, our good old friend, the quotient rule. In fact, the quotient rule is pretty endemic to this situation. So we got to be ready for it. So to make sure that we're on top of things here, I'm going to be careful and play it careful as we work our way through. So looking at our pieces, this is going to be low d high. I should use d dx. Low d high minus high d low. All over low, low. There it is. So looking at all our pieces here, we want to simplify this as much as possible. That's going to be negative 12y, because the derivative of negative 4x is negative 4 with respect to x. This one is going to become positive 12y, positive 12x y prime, because the derivative here is 3y prime, so multiply those together and you get your expression that's up there. Finally, the denominator is 9y squared. And in fact, if you want to, we could go ahead and clean out some of this right off the bat. We could clean out a 3, divide all terms by 3, and we'll get a slightly better looking expression. So we're now sitting at negative 4y plus 4xy prime all over 3y squared. Now this is not going to satisfy us and meet our expectations for a second derivative because of the fact that it's not just in terms of x and y. This has a y prime in it, meaning that we haven't fully simplified this or fully expressed it in terms of x and y. In fact, if I could go back, and I probably will in our assignment when this video is done, I would say in terms of x and y. That is the expectation for when you're working through these problems. So in here, what that means is we've got to back substitute. And what we're going to back substitute is the fact that y prime is the same thing as this. If that's y prime, we can make a substitution into our second derivative, and we can get everything in terms of x and y. It works out really, really nicely. So in looking here, let's see what we got. We get negative 4y plus 4x. Now it said y prime, so that means we're going to be multiplying it by negative 4x over 3y. Again, the reason is that is y prime. which goes by the codename dy dx. In our denominator, yeah, we still have 3y squared. So from here, truthfully, if you're one of those people that's just like, I got stuff to do, people to see, shows to watch, this is the correct answer. Like, there is nothing incorrect about that answer. Totally correct. Assuming you used parentheses and everything correctly and did all your simplifying right. I'm just not going to settle for that as a final answer, though, simply because I think I can do the algebra for it. I don't think it's going to be that bad. The next one, yeah, that's going to be that bad. But this one, not so bad. So in here, what I want to do is first figure out what I'm looking at. So this is negative 4y. This is minus 16x squared over 3y. And my denominator is 3y squared. Now to clean this up a little bit and prepare us for bringing some pieces together, I want to get a common denominator. So I'm going to multiply up and down by 3y. When I do, I get negative 12y squared minus 16x squared all over 3y. And all that is over 3y squared. With that in place, we can now use the fact that we're dividing fractions. Remember, we've said this many times in this course. But if you have a over b over c, that's the same thing as a over bc. It's to flip the second fraction and multiply when you're dividing fractions. So in this case, we're going to end up with, on our numerator, negative 12y squared minus 16x squared. And in our denominator, we'll have the product of 3y and 3y squared, which is going to be 9y cubed. And of course, there's ways you could factor out a GCF of negative 4 if you so desired, but I'm going to actually stop right there. I'm very satisfied with this. This is a great form. It's a single fraction. It's completely and totally in terms of x and y. We've accomplished everything we might actually need for this situation. So again, fairly tough, but again, keep in mind that roadmap. We're going to find the derivative with respect to x first. Then we're going to take the derivative with respect to x of that derivative to get to the d2y over dx squared we want, the second derivative. And then finally, when you get a y prime in your second derivative, back substitute your first derivative, so that way everything can stay in terms of the correct two variables. So there is number 5. And again, this is a basic question. This is probably as basic a question as you can really get outside of a couple contrived examples. But it's still challenging. There's still a lot of computational heft in this work. So don't be discouraged. Just be something to work through. And again, always show clear, organized work, and that should help you quite a bit. Okay, next, this brings us to the question that would have me shaking in my boots. Were I wearing boots, and were my house a colder temperature than it was right now? Well, I try to avoid using AC. So in this case, when you look at it, you're like, no, come on. That's not that much worse. It's not that much worse going on there. Unfortunately, yeah, it is. It's a little bit crunchy. So in order to go through here, let's just work through it and be as careful and organized as possible. I'll try to work in columns, in fact. So our first move, of course, is to find the first derivative. And I would say that that's the part where I expect everyone to be on the same page. I expect you to be able to compute the first derivative here pretty simply. So as we go through, this first term is going to require the product rule. So don't be surprised when we do that down below. I'm not going to do the slow process either. I'm going to do the full, quicker process, breaking this up as 2x times y. Everything else, though, really clean differentiation. So differentiating with respect to x, the derivative with respect to x of 2x is 2 times y, plus 2x times the derivative with respect to x of y, which is y prime. Next, we got y to the fourth. That's going to be minus 4y cubed times y prime. And the derivative of 8 is 0. Always fun to get 0. Okay, from here I want to get all the y primes together. So a couple different ways to do it. I always like to do anything that keeps as many positive signs as possible. So I'm going to rewrite this as 2y equals 4y cubed minus 2x with everything on the right side multiplied times y prime. I'm also going to go ahead and divide away a 2. Hope that's okay. So our equation now reads y equals 2y cubed minus x times y prime. And then we want to solve this. So y prime is equal to y over 2y cubed minus x. So again, if you got there, celebration, great job, that's great work. That's a tough thing to reach. Unfortunately, you're conservatively 30% through the problem. There's a lot more still left to come. So we've got to take the derivative with respect to x of both sides. So our focal point of our attention is going to be differentiating this y over 2y cubed minus x. And you might be able to even see so far why this is going to be a little bit challenging. We've got a y in the numerator, and anytime we differentiate that, we'll need a y prime. So we'd have to back substitute this expression, this complicated dy dx. And second, that denominator has something with a y and something with an x. So we'll actually have two different kind of looking derivatives as we work our way through. Without further ado, though, let's just get started on it. Let's just start to see what happens. So we want to differentiate y over 2y cubed minus x. So again, we are once more using the quotient rule. This is where the quotient rule is coming back with a vengeance. So looking at our pieces, we're going to have low d high. That's just going to be y prime minus high d low. Okay, pause for a second, but yet I'm still on pitch, whatever. If we differentiate 2y cubed minus x with respect to x, that's going to be 6y squared y prime, due to the fact that we differentiated a y, minus the derivative of x, which is just 1. Okay, done. All over low quotient rule. So that's our work. Yeah. Well, we just got to do what we can. We'll do what we can here. So let's see. So doing a little bit darker red. I'm going to distribute this into both pieces. I'm also going to distribute the y into both pieces, just trying to see if we can clean anything up. Let's see. We'll have 2y cubed minus x. Actually, I'm not going to distribute the 1 on the left. I'm just going to leave it there for a second. I'm hoping that'll help us out. So we'll have 2y cubed minus x, y prime, minus 6y cubed y prime. Yes, might work. Minus a negative y. So there's our numerator. We now want to put everything over that denominator. But here's the rub. We've now got these two pieces, both of the y prime. So I'm going to combine like terms there. This will be 2y cubed minus x minus 6y cubed. In other words, we're going to get minus 4y cubed minus x times y prime, all plus y, all over 2y cubed minus x squared. So, okay, we're almost there. Actual almost may vary. So our big piece left here, like the only thing really left here, before we could even put out an expression that is technically accurate just without doing anything, is that y prime. Remember, we said y prime is just equal to this. So in fact, I'll circle the whole thing. That's our y prime. So we need to go into this equation, and we need to plug that in. So, cheating a little bit here. Forgive me. Just already had to do all these on written paper. Y prime is the same thing as y over 2y cubed minus x. So our numerator is now, there's a lot here. Distribute these pieces to both parts here. That's going to make our new numerator. It's our new numerator. Our numerator, maybe? Who knows? This will become negative 4y to the fourth minus xy over 2y cubed minus x, all still plus y, and all over 2y cubed minus x squared. And now again, at this point, let me remind you, this is the correct answer. There is zero wrong with that answer. It wouldn't be sitting there in a multiple choice context, like you wouldn't be able to find that in the answer choices, but it is correct. It's all in terms of x and y. Oh, excuse me. Yeah. It's completely in terms of x and y. That meets everything that's there. Everything's accurate. We're good to go. But again, I'm one of those people that really wants to finish this off in its fullest, greatest glory. So what I notice is that right here we've got this denominator in the numerator, making this complex fraction kind of annoying. We've got that 2y cubed minus x. We also have 2y cubed minus x's down in the denominator of the full thing. So what I'm going to do here, which is probably the ugliest move of the entire thing, is I'm going to multiply up and down to get a common denominator by multiplying up and down by 2y cubed minus x. When I do, my numerator over there still has minus 4y to the fourth minus xy, but now our right side, which will have the same denominator, that's big, is going to be plus 2y to the fourth minus xy. So interesting that there's a lot of similarity in that numerator. That full numerator is now over 2y cubed minus x. Actually, I don't need the parentheses. And then just to remind us, this whole thing, which I have to be careful about the length of that, excuse me, this whole thing is over 2y cubed minus x squared. So finally, in our last step, we can simplify the extra pieces here. So I'm going to combine these guys using that same denominator combination rule that we've used many times. So in fact, I'll do that right now. Our denominator is going to end up being 2y cubed minus x cubed. And our numerator is going to be, we've got, it looks like, negative 2y to the fourth minus 2xy. And of course, if you wanted to simplify that a little bit, you could. I mean, I'd be perfectly happy with that as a final answer. I think that's probably the best one. But if you did want to simplify a little further, you could pull out a GCF of negative 2y. You'd be left with y cubed plus x. And all of that stuff is over 2y cubed minus x to the third power. So I suppose if we wanted to call this the cleanest version, that is probably the cleanest version or the most simplified. But boy, was that a journey to get there. As with the previous example, where it was already kind of challenging because just the length of these problems and the quantity of computation you have to do is fairly challenging and demanding, what I'd point out here is, again, this would be a really tough problem. This probably isn't a test question. This is a good dig yourself in and see if you can keep things organized in your take-home problem sets kind of question. But again, I can't imagine you'd be tested on this particular one during a test. Or if you were, you might be tested on finding the numeric value at a given point, where you could stop at any point and just plug in x and y and make it into a number problem. But still, good problem, and I certainly feel proud of my work on this problem. Okay, that brings us next to question number 7. Now with 7, I'm letting you know right now, I'm skipping part A because I think part A is just simple enough that even if you weren't 100% sure and you felt a little uncomfortable, you could look at the written solutions and understand it perfectly. So in number 7, what makes this question a little bit interesting is how it starts. It tells you to consider the implicit curve, which is not new, but the implicit curve for which dy dx equals 2x plus y squared. So in a sense, what this is they're giving us the slope. So we already know what the rate of change is, what the dy dx is. We already know y prime. They gave it to us. So in a sense, we're starting in a different place. It's in a much cleaner, easier to work with place. They've already done the heaviest lifting for us. So in here, for example, in part 7b, we're asked to compute d2y over dx squared. That's our first task. Well, we happen to know that that's equal to the derivative with respect to x of dy dx. We're just taking the derivative of the first derivative. Well, in our case, that's just the derivative with respect to x of 2x plus y squared. And that's actually a really straightforward thing to compute. In fact, look at it. It's 2 plus 2y times y prime. So at this point, a lot of people just go, yay, look at me, I'm done. But they're not. The issue here, and what makes this a little less than trivial, is we have to find and back substitute what y prime's equal to. But as we said, they gave us dy dx, which is just another way of saying here's y prime. Enjoy. So for us to finish this problem, we need to back substitute the full y prime, which in our case is 2x plus y squared. Make sure you include those parentheses, otherwise you could get the answer wrong and just not even see what you have to do. So with that in place, the answer is done and correct, but I'm going to go ahead and distribute. I'm going to have 2 plus 2 times 2 is 4xy, plus it looks like 2y cubed. And I like that as a final answer. But some of you may want to go a little bit further and factor out a GCF of 2, in which case you get 2 times the quantity 1 plus 2xy plus y cubed. So either of those answers is perfectly acceptable, but there's our second derivative. Now, and the beauty of this, I'll point out to you and remind you, is the beauty is we didn't have to do all of that or all of that. They gave us the first derivative, and it was a really clean first derivative with everything in a nice line. This allowed us to proceed very quickly forward and work our way through the problem. So there's our second derivative. It was just a little bit more cheaply obtained than it was in the past. Okay, next. Question number 7c. Could the graph at right be the implicit curve described here? Explain our reasoning. So in looking at this graph, let me remind you something else as well. Before we start, we only have a few pieces of information here. We know dy dx is equal to 2x plus y squared. And then also, because of the work that we did a second ago, we also know, actually no, I'm going to take this one. We also know this, that the second derivative, our second derivative is equal to 2 plus 4xy plus 2y cubed. So that's basically what we take into this problem and we have to work with. So we've got to use some stuff here. So my first thought, and I'll actually change colors to help us think about this. My first thought here is to look at what part of the graph we have. Like, where are we looking at this graph? Because that's going to be relevant without any points labeled. Well, we are right now in quadrant 1. That's all we can see of the graph. So in quadrant 1, let me remind you that x is greater than 0 and y is greater than 0. So in other words, both x and y are positive. Given that information, this is really helpful. In quadrant 1, you can almost see this. Let's see if I can do this correctly. Boom. That's a little too small. There. So if we're in quadrant 1 with x and y both positive, let's think about what dy dx would be. Well, 2 times a positive number plus a positive number squared is going to be positive. And that implies that the graph, or the curve, is increasing. And I'm going to use C just to call it the curve. I'm just going to call this curve C for the moment. So C should be increasing in quadrant 1. Is that true in our picture? Yep, everywhere there has positive slope, so that's a good sign. Looks like this could potentially be our curve. Here's our second situation though. In quadrant 1, 2 plus 4xy plus 2y cubed would be 2 plus a positive number plus another positive number, means the second derivative is also going to be positive. And if the second derivative is positive, what property does that tell us about a function's graph? Concavity. Yeah, I heard something about concavity. That means that C is concave up. So in other words, knowing what concave up looks like, this graph should be opening upward. It should be an open upward situation. Looking at our picture though, looking at the curve graphed on the right, we're opening downward. So that violates what we were expecting here based on being in quadrant 2 or quadrant 1 with positive x and y values. So unfortunately what that tells us is that this is not true in our graph. Or, so it's like not, I guess it should make it sad, it's confusing. Let's just state what's here. So what we just found out is in quadrant 1, I'm going to abbreviate it here, since x is greater than 0 and y is greater than 0, dy dx is greater than 0 and the second derivative, d2y over dx squared, is greater than 0. The graph, again I'm just trying to translate what we just saw, the graph is concave down though. So d2y over dx squared would be less than 0. So the answer to the question is, could this graph at right be the curve described here? Well, no, it can't, because the second derivative doesn't match. It needed to be positive, and here it's clearly negative. So let's see, could the graph at right be here? So no, that is not our graph, or our curve if you want to say instead. So to answer our question, we had to make sure we answered the question of could it be? No, it can't. And so there's our work. So again, this is one of those little things. This is a tough question. These are tough interpretive questions, but I think the thing that'd be most important here to look at was this sort of inventory work I did at the very beginning, looking at what ingredients we had for our relation, like any information about points, any derivatives at all. And then second, to focus on where we were looking at our function, or our graph, not our function, but our relation, which happened to be in quadrant 1, and then thinking about what that tells us about values and points in that quadrant. That was able to point us out and allow us to find a contradiction to what we'd already found and prove that this could not be our graph. So again, very tough question, a different type of function than we've seen before. I think we only did one problem like this in the past, but a really great question to get you thinking and using the information that's there. So hopefully that cleared some things up and helped you work your way through 7C. Okay, finally, moves us to question D. I was almost going to say quadrant D. So once again, what do we have? So just as kind of an inventory here, we've done this in the previous problem, but just to continue reminding us of what we've found in this problem, we have that the second derivative is that expression, and the first derivative is 2x plus y squared. So here's what we have. Now question 7D asks us, does the curve have a local max, local min, or neither at the point -2, 2? And you might realize, or you might find it suggestive, what we're going to do here is going to involve the second derivative. And the reason for that is, again, we're just limited. Our inventory of things we know about this curve are very small. And you can't even use what we did on the previous problem, because that was in quadrant 1, but the new point is in quadrant 2, thanks to some excellent engineering by the person who just wrote this problem set this morning while watching an episode of Parks and Rec while eating a Cliff Bar that he put in the microwave. So, with that said, we can't go through anything else. We only have the derivative and the second derivative as tools for us to work our way through. So in working here on 7D, we want to talk about maximum, minimum, and neither. Let's just plug in and see what we've got for first and second derivatives. That's just a way to approach this thing. So let's see what we got. So first thing, if we compute dy dx at the point -2, 2, we're going to get 2, or we'll just do it this way. We'll get 2x plus y squared evaluated at -2, 2. That's going to be equal to 2 times -2 plus 2 squared. You might say that's too many 2's, but that's clearly -4 plus 4, or 0. So what we just showed is that dy dx, or the slope of the curve, is equal to 0. And that's actually huge. That tells us that -2, 2 is a critical point. So in other words, although we don't have to say these words on here past the critical point piece, that tells us this is a candidate. We might have a candidate for a relative extremum. So everything's still open here. Having a critical number is essential. You might even say it's critical to being able to answer this question accurately, or to have a local max or local min. So we did our first derivative. Let's next move up and attack the second derivative. So we want to next look at the second derivative itself and evaluate it at -2, 2. Well, recall, as we said, the second derivative is 2 plus 4xy plus 2y cubed. And we want to evaluate this at -2, 2. Plugging in, that'll be 2 plus 4 times -2 times 2 plus 2 times 2 cubed. Ugh, that's a lot of 2's. That's equal to 2 minus 16 plus, let's see here, that's 2 times 8 is plus 16, which is equal to 2. And that number 2 is greater than 0. So what that tells us is that our curve is concave up. And concave up, of course, looks like this. It actually looks like the letter U in the word concave up. So with that in place, knowing that we have concave up and we're at a critical number, the point we're talking about is right there at the bottom of a concave up section of the graph. And that tells us right off the bat that we actually have a local minimum. So in fact, to wrap this thing up, we've done all the essential work. We've really justified everything. But to draw our conclusion, we have a local min. We have a local minimum at -2, 2. And our reason, if we're looking to it, is because dy dx equals 0, which guarantees we have a critical number or a critical point, and the second derivative is equal to 2, or sorry, our second derivative is equal to 2, but it's greater than 0. So by the second derivative test, I hate this part where I just have to write and I don't get anything to say. That's where I wish I had ambient music playing. By the second derivative test, -2, 2 is a relative min. So there's our work. And again, I can't claim that I engineered this question out of nowhere. I believe there's a question like this asked at some point on an AP exam for some situation. But I think the idea itself is really good. Like being able to flexibly go from what we're working with, which is implicit differentiation, to maximization, minimization, and justification using the second derivative test is a really essential skill. So I think this is probably a challenging question just because it feels out of left field, but I also think it's a fantastic question to really see how much you've retained and to see your ability to apply that in new contexts. There is, though, the final part of 7 itself. Okay, so that brings us next to question number 8. And gosh darn it, this is moving really slowly, but here we are. Go as far as I can before the light makes these videos impossible. So in 8, first in part A, we're given a really simple equation. And in fact, part A is probably the easiest question on the entire page. I'm only choosing to do it so that we have the ingredients here. So to get dy dx, we have to take the derivative of this implicitly defined curve x cubed plus 6y equals y squared. Well, I'm not going to belabor the point. We get 3x squared plus 6y prime equals 2y y prime. Moving some pieces over, we get 3x squared equals 2y minus 6 times y prime. And there is our dy dx. It's equal to 3x squared over 2 quantity y minus 3. And so, just so we have it, because I have a feeling the only reasons here is to do the work, there is 8a. Easiest implicit problem that we attack on this problem set. With that in place, and I'm going to paste it in right now, we know from the previous part what dy dx is equal to. In fact, I would write this question, differently if I go back. We're next asked to find all points for which the graph of the curve has a horizontal tangent line. So this phrase, horizontal tangent line, I'm hoping that when you picture a horizontal tangent line, you picture a literal horizontal line. And the reason I say that is because looking at a horizontal line, you can quickly diagnose what the slope of that line is. Since it's flat, it has no actual slant to it, so m is equal to 0. So what we're trying to figure out is when does dy dx equal 0. So in showing your work, this is a hugely important piece, the first thing I need to see is your explanation of what you're doing. If you just set a part of the equation equal to 0, you will lose a point. You haven't communicated well enough where this is all coming from. So what I mean is the first thing I want to see is that statement which describes how you find a horizontal tangent line. It's that dy dx has to equal 0. Hugely important step, you got to do it. If you don't do it on a test and you're like, wait, I didn't know, how did I know? Well, you'll probably be tested on a warm-up quiz at some point, but I'm telling you right now, it's there, you got to be on it. So from there, if we want dy dx to equal 0, looking at an expression here, it doesn't matter what our denominator has, as long as our numerator is equal to 0. So that translates to 3x squared equals 0. And of course, if 3x squared equals 0, that tells us that x equals 0. So in some cases, that would be all you need to do. We found the place where there's a horizontal tangent line. It happens to be at x equals 0. But sadly, that's not all this problem asks for. And I say sadly because I'm really tired and my back's really sore. Get to see the surgeon tomorrow, in fact. But in this problem, what we have to deal with, what all of us have to deal with, not just what me have to deal with, is we have the point x comma y, and we're supposed to find x comma y. And right now we only have x. So that means we need to go back to our original equation. If x equals 0, that means we can take our original equation x cubed plus 6y equals y squared, and we can solve it. So that would mean that we'd have 0 cubed plus 6y equals y squared. That's the same thing as 0 plus 6y equals y squared. And it's the same thing as 0 equals y squared minus 6y. Doing a little bit of factoring work, we can pull out a GCF of y. We'll get that 0 is equal to y times y minus 6. And that tells me there are two potential y values, y equals 0 or y equals 6. And with that said, that finishes our problem. We're going to have horizontal tangent lines at two different ordered pairs, both of them with x equals 0. So 0, 0, the origin, and 0, 6. So I'm expecting that there are actually two. And you know what, let's go check really fast. We haven't used Desmos today's lecture. Why not throw one in there really fast? This is a great time for it. Let's see what we got here. Oh, it didn't work. I need to make Desmos my homepage here. Okay, so what was it? X squared, x cubed. Again, enjoy the fact that Desmos can do this. Plus 6y equals y squared. Okay, so there is our equation, or there's our graph of the function. Let me make it a little easier to read. Oh, reverse contrast is fun though. So there it is. We're supposed to have horizontal tangent lines at 2 points, 0, 0, and I think it was 0, 6. Question is, do those look reasonable? Heck yes, they do. It looks totally flat right there. In fact, if we do this, y equals 0 and y equals 6, look at that. They definitely look like they're tangent in those spots. So it looks like we've done our job there. And that completes for us 8b. 8c then, not surprisingly, then asks us to instead focus on where the graph of the curve has vertical tangent line. We want to find that out next. So next for vertical tangent lines, looking at this piece, I'm going to try to draw it really effectively. It's a really ineffective ending. Oh, come on, really? Whatever. It's an exclamation mark. There, for a vertical tangent line, our slope in this case is going to be basically infinity. We used to call it in Algebra 1 when I took it in middle school, we called it undefined, but really this is going to end up being some number over 0, because there's lots of vertical change, but absolutely 0 horizontal change, which produces this infinite kind of slope. So for our case though, we can't just start by plugging in different pieces like we're supposed to. Let me see what I got. In fact, I needed this here as well. There's our derivative that we're going to use once again. But there's an essential starting point that I need to see in your work, or else you will, again, just like on the last one, lose a point. If we want there to be a vertical tangent line, we need dx dy, as in the reciprocal of dy dx, to be equal to 0. What that's saying is we want no horizontal change over whatever vertical change. Once we have that essential statement in place, then we can tell that's just asking us when does the denominator equal 0. So from here, that would be 2y, 2 quantity y minus 3 equals 0, and that's like the quickest problem out there. That's just that y equals 3. So we know the y coordinate here is going to be 3. Once again, we would be done in just boxing our answer, if not for the fact that we're again asked for the point x comma y. So if we want to actually wrap this thing up, we need to figure out what the x value is that goes with y equals 3. So once again, we take our new y value and we plug it into our original equation. We have x cubed plus 6 times y equals y squared. That means x cubed plus 18 is equal to 9. Means x cubed equals negative 9. And cube rooting both sides, there are a couple different answers that we would accept here, but that means x is going to be equal to negative cube root of 9. So our point where we have a vertical tangent line is going to be at the point negative cube root of 9, comma 3. And just as we did on the previous one, it's worth just going onto the graph and making sure that's actually there. So quick little check. Negative cube root of 9, that's going to be negative 9 to the 1/3 power, comma 3. And look at that. Look at that. That looks just as tangent as we might have expected. In fact, look at that. So we seem to have done a really great job. Hope that doesn't mean anything. Done a really great job. We found all 3 special points or interesting points here. We've done our work, and we have vanquished question number 8. Next, though, that brings us to question number 9. And question number 9 is the last one that has no calculator. It doesn't allow calculator. And I've omitted part 9a, question 9a, simply because I think that's a really simple question. It's just a plug and chug situation where you plug in an x and a y and solve for the c value that's there. For us, though, the questions for B and C are slight variations of what we've just been doing. We're asking you a question about a vertical tangent line, sort of, in the derivative, but we're not giving you, like, just solve a simple equation. There's a little bit more here. So, for instance, in 9b, you are asked to prove that the curve has no vertical tangent lines. So, no vertical tangent lines would be the same thing as saying dx dy does not equal 0 ever. I wanted to do it in the Sandlot voice. Ever. So it never equals that. It's just not going to happen. So in order to get there, and in order to look at this, we need to figure out what dy dx is equal to first. So I'm going to start by quickly taking the derivative with respect to x. I have 3y minus sine y is equal to x squared plus c. With c just being a number, when we take this derivative, we'll obviously get 3y prime, get minus cosine of y times y prime. We'll get 2x plus 0. In fact, solving this all out, I'm going to let you be okay with this quick solving. You're going to get 2x over 3 minus cosine of y. So there is our first derivative, dy dx. So the question we were supposed to ask was, when does dx dy equal 0? So let's see what that would mean. So if dx dy equals 0, that would be the same as telling us that the denominator equals 0. So the question we have is, can we solve this equation? And the answer, of course, is no. Cosine of y is between 1 and negative 1. Just like sine, they're both bounded up and above by plus or minus 1. So with that said, cosine of y never equals 3, which is what would come out of this equation if we were solving it. We'd need to find the y value where cosine equals 3. Since cosine never equals 3, it's kind of our explanation. Since cosine of y does not equal 3, 3 minus cosine of y does not equal 0. And, most importantly, dx dy does not equal 0. Thus, or therefore, no vertical tangents. So in this case, we were in a situation where you just had to know, you had to remember that cosine was a bounded function, and its values were limited to the range from -1 to 1. And that meant that we could never get a large enough value to allow us to have any vertical tangent line. So again, there's less intense math here. There's not a ton of exciting things happening here outside of the implicit differentiation. It's pretty easy, actually. But thinking about what we know about that function cosine and focusing on the denominator as well allows us to determine that there will never be a vertical tangent for this curve. And in fact, if we check really fast here, I've got to turn off all these functions, all these pieces. We have 3y, I think it was 3y minus sine of y equals x squared plus, I don't know, let's just give it a number, plus 1. If you look at this thing, is there ever a vertical tangent line? No. Look at that. It's just kind of slanted the entire way. It's decreasing on the left, increasing on the right. Looks like for sure there's never a place where there's a vertical tangent. Okay, finally, the last part here is actually drawn directly out of the previous one. They're very connected, and this is the kind of question that actually appeared on the 2019 AP exam for AB. There was a question that involved something a little bit like this, or maybe it was a practice exam, I don't remember. Something like that. So I'm looking here. It says, if x equals 9, find the range of possible values for dy dx. So before we do that, let me go steal the derivative one more time and just remind myself what it was, since that way I don't have to recalculate it. So first, it says x equals 9. So if we first and foremost evaluate this at x equals 9, we get that dy dx is equal to 18 over 3 minus cosine of y. So that's a good starting spot. So from here, the next move we're going to make is very similar to what we did on the previous page to determine there were no vertical asymptotes, or vertical tangent lines. What we have to think about, or what we're going to think about next, I'll draw a semicolon so it's kind of separate, we have to remember that cosine of y is in itself bounded. Cosine of y is always between -1 and 1. If that's true, then there are only so many values we can get out of our dy dx. So think about it this way. 18 over 3 minus cosine of y is going to have to be between 18 over 3 minus -1, and of course we're choosing -1 on this side, so the denominator will become bigger, which makes it an overall smaller value, and it has to be less than 18 over 3 minus 1. With those in place, what we've just done is we've just found a way to bound dy dx. dy dx is always between these two values. And those two values happen to be, let's see, this is 18 over 3 plus 1, so 18 over 4, which is 9 over 2, or 4.5. And on this side, we get 18 over 2, which is 9. So what they're telling us is that the slope is always between 4.5 and 9. Doesn't matter where we are on this curve. If x equals 9, the slope has to be between those two. And again, this doesn't necessarily help us right now because we're talking about a specific point, but it is pretty valuable to be able to determine for ourselves that there's only so many values that our slope can get. And in fact, if this had been a different function of x, like say 5x or something, we could have actually bounded the entire equation's slope and found some information about our curve out. So for now, just to remind you and kind of like reiterate the philosophy of asking this question, the goal is to invoke for you that reminder that cosine is a bounded function, and then to let you demonstrate for us that you can show that that bounded function creates a bound for the derivative as well. So again, challenging a little bit different feeling, but definitely something you're capable of handling. So hopefully this helps you handle it the next time it shows up. Because it's going to. Okay, that brings us to our final question, and also the first and only question on this assignment that is calculator active, where you're actually going to need to use your calculator to work your way through things. I think that even part A, which is just asking for the normal line to the curve, is actually in itself a little bit challenging. It takes a little bit of work. So just kind of keep that in the back of your mind as you're working through these. These can feel really cumbersome and feel a little awkward the first couple times you do it, but it's something that you're going to get better at the more you do it. So, yeah, do more of it and get better. So in our situation here, we are told that there's some curve x squared minus cosine of y equals y cubed plus 5x minus 3. And our job is to write the equation of the normal line to the curve at the point where x equals 5. So a couple different pieces that are in here. So the first thing we have to do is, of course, take the derivative. But once again, this is one of those situations where I think the implicit differentiation is actually probably the easiest part of the problem. I think it's the most accessible at the very least. So taking our derivative, there's nothing fancy here. That's 2x. It's going to be minus a negative. So plus sine of y times y prime equals 3y squared y prime plus 5. And doing a little bit of rearranging. Sorry, I'm moving through this really fast. I just feel like these basic derivatives are things you've mastered at this point. I don't want to waste your time if you're watching these videos. So 2x minus 5 over 3, let's see if I do this correctly. Over, if I did that way, that would be 3y squared minus sine of y. So there is our derivative. So that's a great starting spot. Now, as usual, we want to evaluate this derivative at a given point. But once again, we're only provided a single variable. We only know that x equals 5. So as we've done many times today, we've turned to our original equation. They tell us what the relationship is between x and y, even if it's not explicitly defined. So we can plug it in. So for instance, that means 5 squared minus cosine of y equals y cubed plus 5 times 5 minus 3. So although we don't have to simplify, we have calculators and such, which we'll get to in a second. We can clean this up just a little bit. That's 25 minus 3 or 22. We can rewrite this entire equation as 3 equals y cubed plus cosine of y. So this is what contains the value we're looking for, or potentially more values. There could always be more values. We don't know for sure. So we want to try to figure out what is y equal to in this case. But if we want to solve this, remembering that we don't have access to Desmos on an AP exam or on a test for this class, if we want to figure out what y is equal to, we're going to have to use our graphing calculator. So let's pull that up really fast. Let's get that thing around here for us to look at. Here's the problem. We don't have the ability to graph functions that have y's in them. So finding an intersection here to solve this equation isn't going to be practical in the same way we could. What we can do, though, is we can realize that this equation right here, and what we have to realize, it's a better way to put it, what we have to realize is that this equation can be solved on our calculator using intersection, as we have so many times before, if we just pretend like this is an x, and then remember that what we're solving for on the calculator is going to be the x-coordinate, but what we're really finding is the y-coordinate. So it sounds a little bit weird, but in a sense, we just want to treat it as some dummy variable. We don't care what it is. It might as well be t or m or something to solve for. So let me illustrate what I mean. So we want to find the intersection between 3 on one side and then y cubed plus cosine of y. But again, we don't have the ability to graph y's, so I'm just going to graph x cubed plus cosine of x. So I'm going to find the intersection, and remember, since the y is what our x is, or what x is supposed to be as a y, whatever the x values of the solutions are, those are going to be our y values. So let's zoom 6 this and graph it and see what happens. Oh, cool. Look at that. There's just a single intersection point right there. So second calc, we'll go down to intersect. Enter, enter, enter. Oops. So it looks like there's a single intersection point. And down here, like, keep in mind, it tells us, and I'll even copy this into our work here for a second. Where'd it go? I'll even copy this into our work. So it tells us that our solution is x equals 1.417. But remember, we're talking about y's. We're solving a y equation. So in a sense, we need to remember that that's not really x. It's y equals that thing. So the y value we want is 1.417323, and then ... You're noticing that I'm keeping it exact here. And in fact, I'm going to go even a step further on my graphing calculator. That's my x value, 1.417. I want all its accuracy because I know to get a normal or a tangent line, I need to plug that x or y value into the slope. So remember that your graphing calculator stores that value we just found as the x value, but I want to store that as some other letter so I can just pull it up really fast and not have to type in a whole bunch of decimals. So I'm going to take x and I'm going to store it as alpha a. Then when I press enter, anytime I pull in an a, we're going to be able to solve this. And then going back to my work, since I've defined it as a in my calculator, I'm going to go ahead and just say that this value is equal to a here as well. So just to give us a little bit more room, we've just found that that's, geez, there's no room to write it. Oh well, just deal with it. This is going to be equal to A. So I'm going to call it A from now on, so that way we don't have to keep dealing with this work. So that means our ordered pair that we have in question here, now that we have it as defined as A, our ordered pair is really 5, comma A, knowing that A represents 1.417323, etc., etc. But then to get our slope, first the slope of the tangent line, to begin working, we need to plug in the point 5, comma A. So doing so, we'll get 2 times 5 minus 5 over 3A squared minus sine of A. And again, our calculator can do that heavy lifting for us. So I'm going to move it over to the side a little bit. The value we want is that one. The computer's really struggling right now. So let's do math fraction. We're going to have 2 times 5 minus 5, which is 5. I can simplify that. Then we're going to have 3A squared minus sine of A. Oh, crap, I hit that button wrong. Sorry. My mouse is not functioning right now for some reason. Okay, and then we want alpha A, parenthesis, there we go. And this will give us our value. It tells us that our slope is 0.9924 something something. 0.9924 stuff. So there is our slope. That is the slope of the tangent. And it's important for me to re-clarify that, because otherwise I'll very quickly plug it in and just do the slope, or do the equation of the tangent line. So remember, if that is the slope of the tangent line, you have to ask yourself, how do you find the slope of the normal line? Well, the slope of the normal is perpendicular, or the normal line is perpendicular to the tangent line, which means that their slopes have to be negative reciprocals. So our slope of the normal line is going to be -1 over 0.9924, etc., etc. And once again, taking advantage of my calculator's ability, I'm just going to do -1 divided by that previous number. And it gives me -1.0076, which is approximately -1.008. And with that slope calculated, we have enough to finish out our problem. So to finish this normal line equation that we were asked for so long before, our normal line is going to be y minus the y value. So you could write A. That would be acceptable since we formally defined it right here. Or you could write the approximation 1.417. And it's okay to use approximations at this point because it's a final answer. It's not an intermediate calculation. It's equal to -1.008 times the quantity x minus 5. And again, just writing the normal line equation has never been more challenging, but our graphing calculator allows us to get a lot of that work done. And of course, we had to be a little flexible and like solve an equation in x on our calculator, knowing that it really meant y, but the process is accurate. So just remember, you can solve any equation for a single variable in your calculator. You just have to remember with which variable out of x and y on the calculator means what. Everything else here, classic normal line problem, good stuff too. Okay. So we're moving on to question 10b, and I'm going to tell you right now, 10b ends up being the single most cumbersome question of the assignment. It's not the most computationally difficult, it just takes a long time, at least a lot longer than I'd like it to. So I apologize in advance for the difficulty. And I'll let you know right now that if you're watching this, I would perfectly well accept if you simply found the y coordinates where this happened, and you just kind of settled for finding one or two of the x coordinates. Maybe even just a single one, because again, this turned out a little bit harder. What I needed to do is I needed to change that 2 into an odd number, so that way things cleaned up a little bit better. But since I didn't think about that till after I'd done the huge amount of work for it and found all 4 points that end up having the vertical tangent line, it wasn't possible. So keep that in the back of your head. For the moment though, I'm going to try to demonstrate everything that I can here. Just know that it feels like overkill, and if it does, it is. It just turned out a little bit worse than I wanted it to. So first of all, we're talking about vertical tangent lines. So to get there, we need to pull in our derivative. So I'm going to go grab it really fast, so that way we have it handy. So there's our derivative. And I'm just going to kind of toss it up here for the moment. We're going to be using it in a moment. So we're talking about vertical tangent lines. In other words, places where the slope is undefined or infinity, which means we want our denominator to go to 0. Our formal way to write out what we're doing with vertical tangent lines, though, is of course that, geez, why am I having trouble writing this on here? There we go. dx dy has to equal 0. And if dx dy equals 0, that tells me that 3y squared minus sine of y has to equal 0. So we're looking to find the zeros of this equation. Now right off the bat, I'll tell you this much. Y equals 0 is one such solution, because sine of 0 is 0, and 3 times 0 is equal to 0 as well. So that gives us our first one. Unfortunately, there's actually a second y value that's out there that we're going to have to find. So let's find that one first, and let's turn to our graphing calculator to help us handle it. So we're trying to solve and find the zeros for 3y squared minus sine of y, so we can get rid of all that extra stuff we had before. And we're going to go put in 3y squared minus sine of y, but remember, in the graphing calculator, we can't use y, so we're just going to change it and translate it to 3x squared minus sine of x. And then any x values we find for the zeros are obviously going to be the they're going to be the y value we're looking for. So in this case, I want to find the zeros, so I'm going to go zoom, oops, not zoom 0, that didn't work. That backfired. Zoom 6. So we want to find the zeros in there. To me, it looks like there's only one from this direction, so let's make that window a lot smaller. Let's go -2 to 2, and I don't know, let's try -2 to 2 as well. Maybe this will work. Still kind of small. I'm going to go even closer. So part of the problem is that I'm not able to wear my glasses when I make these videos because of glare. So I can't really see what's happening. There we go. Aha, look at that. We have 2 zeros. We have one right there at the origin, the 0 one that we were looking for, and then we have a second 0 over there. So let's go find that second 0. Let's go left bounds right there. Let's go 0.6 will be our right bound, and then we'll guess the value somewhere in the middle. And it tells us that our other x value, which again we are translating to y values because we are solving a y equation just with an x-enabled calculator, is going to be 0.327409. 0.327409, and then other stuff. Now, just as we did in our previous one, because we're going to need to use that value again, I want to give it a name that I can call it multiple times going forward. We already used a in the previous problem, so I'm going to define this as b. I'm just going to call it b from now on. That's that second y value that's out there. And in order to help us with that, I'm going to let the calculator store it as well. So recall that if we press X after leaving that menu, it stores the 0.327 value with all its decimal accuracy for us. So I want to have the calculator let X be saved as the variable b. So that way I can just plug it in as a point wherever we need to. So we now have our two y values, y equals 0 and y equals b, which is what we're going to call it from now on. Now we're supposed to find the points. If we're going to go that far, we're supposed to find the points. So that means we need to figure out what x is when each of these equations has those y values. So I'm going to translate this into two separate pieces. I'm going to do first y equals 0 in green. So if y equals 0, what does that do to our original equation? Well, we get x squared minus cosine of 0 is equal to 0 cubed plus 5x minus 3. So solving this a little better, that's the same thing as x squared minus 1 equals 5x minus 3. Now I want to solve that equation, and I want to do it on the calculator. Like, you could factor this one theoretically, but it would require the quadratic formula because I didn't work hard enough to make sure it didn't. It did. So from here, we're just going to solve that really quickly on the calculator, or, you know, hey, quadratic formula, bu. So in here, we can clear that out. We've got x squared minus 1. We've also got 5x minus 3. We want to find their intersection, so we'll go to zoom standard. I see one intersection down there, so that's valuable. But unfortunately, I'm missing the second one, and that's somewhere up top in the first quadrant. So I'm going to change my window. I'm going to go to -2 to, it looks like, I don't know, let's keep it at 10. And then for the y values, I'm going to go -2 to, let's go 30. See if that works. That's really hard to see. Let's change our window one more time. Oh, I went 330. That's why it was so hard to see. I can tell you, my computer's having trouble with pressing buttons right now. Okay, so we need to find the intersections there. And keep in mind, since we got x value equations and we're looking for the x values, we want the actual x coordinate this time. So let's find them. Second calc, we're going to go to intersect. Yes, yes. And then let's guess the one down by 0. It says that intersection point is at x equals 0.438. I think it was 438. Yep, so I'm just going to leave approximations here for the sake of time. Our first one is there. Our second x value approximation will be the second intersection point, which enter, enter, and it looks closer to 5. It says that one's at 4.562. And so what we've just found is that y equals 0 corresponds to 2 separate points. And that means the ordered pairs where there's a vertical tangent, 2 of them, are 0.438, comma 0, and 4.562, comma 0. So we have 2 points that where the graph will have a vertical tangent. Sadly though, for the sake of me sitting here uncomfortable, we also have a second y value, y equals b. So our second option is we need to look and see what are the x values, or x value, depends on what it is, when y equals b. So going in here, the equation will read x squared minus cosine of b equals b cubed plus 5x minus 3. That's going to give us potentially 2 more x values. So let's go again into our calculator and let's graph that equation so we can try to find the intersections. In this case, we have x squared minus cosine of b. Remember, we defined b before, so we should be fine. This one will be, yeah, I wish I could hear you laugh. I just imagine you're laughing. So b cubed plus 5x minus 3. So let's graph this thing. Oh, good. The same window actually gives us a good picture of what's there. So we once again have, it looks like 2 solutions. So once again, we find the intersections. So one potential intersection point is 4.557. Again, if we're going to use these in some sort of calculation later, we could, store them, but we're not going to. So enter, enter, and I'll do the same thing I did before. I'll guess it's close to 0. And it is 0.443. So with those 2 x values found, we find our other 2 points where these actually occur. And this time we've got to go x comma y. So I'm going to go 0.443 comma our y value, which I'm going to go ahead and leave as a decimal to be consistent. We could actually put b in there. That'd be fine. And then our second one was 4.557 comma b. And so all that work was necessary. Again, this was my fault for writing a question that took a lot more effort and took a lot more solving than I intended it to. But it's not bad. It's really a good question that lets you see how this could work. It gives you a good involved situation where you've got to really think about what these intersections look like. But, challenging for sure. Okay, and finally that brings us to our final question on here. And interestingly enough, the final part, 10C, is similar to the previous one, but much, much easier to solve because, as it turns out, there's only one intersection for each possibility. So in looking here in part C, we're asking you to find the points at which the curve has a horizontal tangent line. And again, we've got the same derivative that we had before. So let's just keep that present just so we're ready to go. And since we're asking about a horizontal tangent line this time, reminder that horizontal tangent lines have a slope of 0, which means in our case, we're looking to solve the equation, or solve and find out when dy dx equals 0. And remember, if dy dx is equal to 0, that's the same as saying the numerator is equal to 0. And oh, thank you, in this case we don't even need a calculator to solve this. Clearly there's one such x-coordinate where the derivative is equal to 0, and it is at 2.5 or 5/2. So right off the bat we're in much better shape than before. We found the single x-coordinate where there is a horizontal tangent line, but of course we always remember that there could be multiple different points where this happens. There might not be, but there could be. I mean, the last one, we had 4 freaking points. So in this case, we need to go ahead and go back to our original equation and see what the y value is that goes along with it. So in looking here, our equation was x squared minus cosine of y equals y cubed plus 5x minus 3. Let's plug it in. So x squared minus cosine of y equals y cubed plus 5x minus 3. Now, of course, I'm going to let my calculator do the heavy lifting here. We're going to call these y1 and y2. And we're going to find our intersections. And someone might argue that I could simplify this better or rewrite it in a different way. I've done enough of that today. We're going on almost 80 minutes of this video. And this isn't good sitting. So let's take a look here. Where's my calculator? There you are. Okay, graphing calculator, help me out here. So new equations to work through. Once again, you're probably old hat at this point. You're comfortable dealing with the fact that we're going to be putting x's in but solving for the y values. So this is 5 halves, or 2.5 squared, minus cosine of y. Again, we're hiding it as an x here to let our calculator, trick our calculator into finding y values. So it'll be y cubed plus 5 times 2.5 minus 3. So we want to find the intersections of these things. And I don't know where these answers are going to fall, so let's just pop it in there. Oh, look at that. Looks like we've only got a single intersection point. So nice. So we just need to find that intersection point. So intersection is going to be right there. Enter, enter, enter. There's only one. So now be careful here. This is a place where you could get caught a little bit. Our intersection is -1. Here, I'll even put it in there and paste it in, just so we can see it a little better. And by we, I mean me, because I can't see. So here's what we got so far. We did that work. There's what our calculator spit out. But now we've got to be smart about this. We put in equations that look like, look at that on the screen, x cubed plus 5 times 2.5 minus 3. But remember, we let x play the role of y. So this is really our y value, and this is meaningless in the situation that we're looking at. Our y value is -1.4929. So that means the y we're looking for is approximately -1.493. And that means the ordered pair we were looking for is going to be 5 halves, comma, -1.493. And there is our point. So allegedly, there should be a horizontal tangent line at that particular point. And now I haven't looked at this graph to see if that's actually true, but you know what the heck, we're here. Let's throw it up there once and just see what's happening. So I'm very curious. So our equation, x squared minus cosine of y equals y cubed plus 5x minus 3. So let's see what actually happens here. Maybe some of these points aren't actually there, or maybe it's just really hard to see. So for instance, horizontal tangent line, we have 5 halves, comma, -1.493. Does that look pretty good? Oh yes, that looks pretty good. So I'm pretty confident that we've done a good job there. The question's going to be, did we do a good job with the vertical tangent lines? Because looking here, it's a little ambiguous whether we got them or not. So let's go grab a point from the previous one and just take a look. So again, we're done with the problem set. Everything's there. I just want to look at these points. So 0.438, comma 0. 0.438, comma 0. So does that look vertical? Yeah, actually it does. It looks pretty vertical. 4.562. That also looks pretty vertical. So I'm not upset about that one. Those two look good. What about the other ones? 0.443. Ooh, look at that. What was the last one? 4.557. So looking at these guys, do they look like they might actually be candidates as well? You know what? It's kind of hard to see, but I could believe that. I can believe the fact that it's really vertical at that point and vertical there, and there's some sort of concavity change that's happening there. It may require a little bit of extra analysis to be able to be convinced, but they don't look unreasonable at least. So you know what? Because I'm done and I don't want to sit here anymore, I'm going to go ahead and say we just kicked the butt of this problem and we've got everything complete, and it all checked when we looked on Desmos. So thank you for watching. Mercifully, this is over. I hope it was helpful, because if it wasn't, I've just wasted a couple hours of my summer. Have a great night.